Hello, my name is Jim Gates, and welcome to this course on string theory. Our universe is a very interesting place, and scientists for several thousand years have been trying to understand it. We have reached a stage where some things we understand, and yet much more we don't. One of the places that this quest has taken us is to a place called string theory. String theory is not really physics yet. It's mathematical physics, it's theoretical physics, but we have not seen it in the laboratory. Whenever I give a lecture to the public on string theory, I actually like to first start with some physics. So we're going to start with some real physics and then use this as a background to move to string theory. In our universe, there are binary stars. These are two stars that orbit one about the other. And sometimes these stars undergo some very strange transformations and turn into things called neutron stars. Neutron stars have magnetic fields about them, and they emit particles. We have a movie watching such a binary star system. And here we are. You'll notice the balls, those represent the stars. The markings around them are the magnetic fields, and the beams that come out of the top and bottom are beams of high energy particles called gamma rays. You'll notice there's one other feature in this movie. There was something that looked like water. So let's imagine we could surf whatever that substance was and follow it as it goes through space. As we look at the stars through this substance, it distorts their light. And if we look below, it does the same. But if we ride for long enough, what we will find, perhaps, is that this wave of whatever might encounter the Earth. So here's the Earth and its companion, the Moon. And we're going to watch this stuff as it comes down from the heavens and has an impact on Earth. What would that impact be? That's the question. Well, propagation of this wave will come down out of the sky, and if it does so at two places in the United States, it'll find large L-shaped buildings. These are called LIGO, the Laser Interferometry Gravitational Wave Observatory. And as you can see in our small movie, the waves cause the buildings to move, which is, of course, quite interesting and marvelous, and it sounds like science fiction. Yet, our country has built these two facilities at a cost of about $400 million, and we're going to try to see if these waves are there. So you might ask, well, where do you get the ideas these waves exist? Well, this takes us to the realm of theoretical physics. And for this purpose, let's go back and think about string theory for a moment. What is string theory? Well, in a nutshell, the idea of string theory is that the smallest, most fundamental objects in our universe are not things that look like little balls, as we had thought for about 2,000 years, but instead these small objects are like filaments of spaghetti. In fact, I like to call them pasta. So let's take a small journey so we can begin to see where these objects are. All of my journeys will be computer animations which represent mathematics, and we'll come back and talk about later how this is possible. So here's a movie about shrinking in size. This is what I like to call the scale of size movies. You'll notice there's a bunch of marks on what looks like a clock face. Each one of those means to shrink something by a factor of 10. So for example, if I start with a meter stick, something about this long, cut it into 10 equal pieces, throw away 9, keep 1, I get something about that long. I do that process again, and I get something about the width of my fingernail. If you do that 10 times, you get down to the size of the atom. So this movie is about shrinking like that, and each one of these marks that you see on the clock face is 1 power of 10 smaller. So here we go in our movie. We're going to start shrinking. We're going to go fast at the beginning because, well, there's lots of interesting things like molecules and chemistry at that level, but we want to slow down at the level of biology. So here we are at 10 to the minus 5. And what you see here are animations of newly created blood cells with their nuclei still intact as they emerge from bone marrow. At 10 to the minus 9, we encounter the world of strands of DNA. And of course, this is what the Human Genome Project has taught us most remarkably to read as the book of life so that we can get insights into our own genetic structure. At 10 to the minus 10, we enter the realm of the atom. This is what atomic physics is about. We encounter here an object that is the atom. These blobs around the object are its electron clouds, but we're going to continue to shrink in size. And at 10 to the minus 12, 10 to the minus 13, 10 to the minus 14, and 15, we encounter the world of the nucleus. Here we see two blue balls, those represent protons. The little pink balls represent neutrons. And as we continue to get smaller, we catch glimpses of something inside. Those things are called quarks. But now let's keep shrinking in size. And now we leave the realm where instrumentation can tell us about our universe. We continue to shrink. And at these smaller levels, we don't really know what's there. We have no instrument that will tell us that what is at these levels. However, for about 30 years or so, there have been mounting bits of evidence, mathematical evidence, that our universe at the level of 10 to the minus 35 meters or 10 to the minus 34 meters is described by these little filaments, and they're the most fundamental objects that possibly exist in our universe. In fact, they may well be the DNA of our universe. So this is the realm of string theory, and these lectures are designed for us to get insights into what physicists have been able to glean from the mathematical vistas that are presented about this. So that's what string theory is about. But why would you want such a strange picture of the universe? Well, in order to answer that question, let me go back and talk about attributes of the universe that are fairly well established. For example, we live in a universe where it seems pretty clear that about 14 billion years ago, maybe 13.5, an event occurred which announced the birth of our universe. This event was called the Big Bang. There are, in fact, lots of confusing statements about the Big Bang. It is, first of all, a piece of mathematics. It's something that two physicists, Georges Lemaitre and a Russian physicist by the name of Friedan, were the first to understand that Einstein's equation said that at a certain point, something very strange happens, and that very strange event turns out to be the creation of the universe. Well, the Big Bang could, first of all, actually not be heard for a very simple reason. To hear something, you need to have air molecules. When the Big Bang occurred, there were no air molecules. They hadn't been created yet. So it's a mistake to think of the Big Bang as an explosion, because it's not a literal explosion in any sense that we're familiar with. In fact, even the name the Big Bang is kind of a joke. An astronomer by the name of Fred Hoyle absolutely abhorred the idea of the Big Bang. He thought it was just ridiculous nonsense. And so in order to give it a derisive name, he called this piece of mathematics the Big Bang. But the name stuck, and the theory has gone on to become the dominant view of how our universe works. So there was this event, we call it a singularity. The equations describe this very strange behavior, and out of that event seems to occur our entire existence. Space and time are created, matter and energy are created, and the universe at first is a single place. Well, fortunately, that situation didn't last very long, because we wouldn't be here. In those conditions, densities and temperatures were enormously high. In fact, they were so high that you couldn't form atoms. If you tried, it would be like taking water and putting it on a hot pan. You know what happens? It turns to steam. Well, in the very same sense, atoms placed in the situation of the primordial Big Bang would simply disassociate. And in fact, they did disassociate, so much so that light, in fact, could not propagate in the universe. And we have here a movie that is running about some possible ways this happened. Now, the first person who actually allowed such pictures to come to our species was Albert Einstein. In 1916, he wrote a masterful equation, which is called the theory of general relativity. This theory of general relativity said that at some point in the past, well, actually it said several things, but one possibility was at some point in the past, a universe burst into existence, we see it here, and continued to expand forever after at a constant speed. Now, Albert Einstein was a great scientist, but he was also a good scientist. And good scientists remind me, as a physics professor, of good physics students. And one thing that physics students learn to master very quickly is something called the fudge factor. Albert Einstein knew how to use fudge factors. And so when he wrote his equations, he wanted to get a picture of a static and eternal universe, because that's what the astronomers told him ought to be described. But instead, his equations described a universe that was exploding into existence and then growing. By introducing this fudge factor, which we now call the cosmological constant, he was able to have a fixed bubble for the universe. But there were other possibilities about the behavior of the universe. Maybe after a Big Bang, it could crunch back to form a big crunch. Or maybe it could slow down as it's expanding. Or perhaps this middle possibility, the universe comes into existence and then after a certain time speeds up in its expansion. And by the way, this middle one seems to be the universe in which we live. Now, our universe has other strange attributes about it. And what string theory has to do if it's to be a successful theory of nature, is to describe all of these strange attributes that I just described in terms of the Big Bang. Well, what else is there out there that string theory has to have as a challenge? Well, there's something called dark energy. Dark energy is the thing that's speeding up the expansion of the universe. And if string theory is to be successful, it has to explain dark energy. What else does string theory have to explain? Well, there's something even more mysterious called dark matter. Now, I have a different movie to try to represent dark matter. You'll see in this film two sets of planes with what we take as models of stars. So imagine that you could take stars and spread them out on a table. That's what these squares are. And at a certain time, imagine taking the table and giving it a twist, and there's no friction so that when you give it a twist, the table keeps on turning. If the stars are gravitating, you would say, well, gee, the stars should pull themselves together because gravity causes things to attract. So let's run this movie and see what happens. So you can see on the right-hand side, the two tables are turning, and gee, the stars are definitely starting to contract. They're getting closer and closer. And in the upper one, if you'll notice, it is very quickly coming to form a shape that has some reminiscence of a spiral galaxy. Well, we live in a spiral galaxy, so we're pretty happy. You'll notice that in the lower picture, the same process is going on, but it's happening much more slowly. Well, let's go back to the top one where we see something that looks like a spiral galaxy. It looks like our mathematics has described our universe, but wait. Look, the galaxy's falling apart in the upper picture. The only way that the lower picture differs is you get a galaxy, and the galaxies in the lower pictures live on the lifetimes that we see galaxies in our universe. So there's definitely something different about these two pictures, and the difference is this stuff we call dark matter. String theory has to explain why you get these different behaviors of galaxies. Why? In fact, what is this dark matter that causes galaxies like the type we live in to be stable over the amount of times that we've seen? And then finally, there is the expansion of the universe with dark energy. We've talked about the Big Bang, and we need dark matter. String theory's got to do all of these things, and that's the most remarkable challenge, perhaps, that it faces. Now, of course, string theory is science, so let's spend a moment talking about how science is able to take us to these realms where we have no way to access with our instruments or with our senses. You see, science is, first of all, a man-made construct. It consists of three parts. Two of the elements are objective reality and the human imagination. The human imagination is a vital place where we get our stories, our mythologies, but it is also the primary agency by which we are able to understand the universe. Now, you'll notice in the picture so far, the imagination and objective reality are separate. If that were the case, we could never do science. But fortunately, we can imagine the universe. In fact, Albert Einstein once said that imagination is more important than knowledge. And he was right, because it is our capability to imagine how the universe works that leads to science. And there's one other element of science that's important. Namely, we have to have the technological capacity to distinguish between our imagination on the one hand and objective reality on the other. So this is what science is all about, and that's what we do as scientists. We work in this overlapping region where the human imagination, technological capacity, and objective reality are all together, and science does not exist outside of this region. We can imagine things, there are things in the universe we don't understand. So that's in the region over here. On the other hand, I can imagine pink elephants and green fairies. Well, I've never seen those in the universe, so that belongs in the human imagination. So string theory is a construct of the human imagination. But the thing to understand that's most important is that mathematics is an element of the human imagination. It is with mathematics that theoretical physicists probe the structure of the universe in the hope that we're not working in the region that's solely of the imagination, but in fact sits in the overlap region. And when we get it right, marvelous things occur. Well, what kinds of marvelous things? Well, this computer, for example. This is an example of imagination. 30, 40, 50 years ago, no such device existed. But it does now. It makes our life easier. Most of us spend enormous amounts of time making our living using these things. And yet, this is a product of imagination. Now, the other part, as I said, that's really important in this is mathematics. So we have to explore a bit how does mathematics come into this story. So let me take you to some mathematics. This is what scientists who measure things get. They get pictures like this. This is data. Now this data is particularly interesting. It's what we scientists call the concordance model. This is a picture of our universe. What's data is actually here? Well, at the bottom you'll see there's a pie chart. What this pie chart tells us is the amount of energy in our universe and how it's distributed. It turns out that roughly speaking, 70% of the energy in our universe resides in dark energy, this stuff that's making the universe speed up in its expansion. About 25% of this energy in our universe is this dark matter which causes the galaxies to be stable. Only 5% of the pie chart is ordinary baryonic matter. And why should that surprise you? Well, you see, that's us. We're made of protons and neutrons. That's what scientists call baryons. So it's these kinds of plots, when they are represented in terms of mathematical equations, that theoretical physicists try to get the right equations for. So that's what theory is all about, and that's where mathematics enters. Well, mathematics plays one other interesting role for us because it also frees our imagination. It tells us things that we have no way of knowing otherwise. For example, that Big Bang that I told you about was followed by a period when the densities were so high that light could not propagate. Well, it was a very strange universe, very small. At a certain point, it spread out enough so finally light could travel through the universe. When this happened, a first dawn occurred. You can think about it as being the first morning of existence. The light leaves what we physicists call the surface of last scattering and goes streaming through the universe. In the 1960s, some of this light was detected. Two scientists, Arno Penzias and Robert Wilson, were operating a device called the Big Ear in New Jersey. And they listened to the universe and they heard a kind of static. For a while, everyone was puzzled by what could be the source of the static. Well, this was fairly close to Princeton University. And at Princeton, there were scientists who had been studying Einstein's equations for decades. And one of them had understood that these equations predict that if there was a Big Bang, there must be afterwards a kind of sizzling that you can detect everywhere in the universe. We now call this sizzling the cosmic microwave background. And the cosmic microwave background is a glorious structure that exists everywhere when you look up in space. It's kind of a fossil. It's a snapshot of our universe when it was about 300 years old, 300 million years old. 300,000 years old. We live in a universe where a snapshot was taken of it when it was a toddler. To me, this is a marvelous place to be in. And this is one of the reasons why scientists are becoming increasingly convinced that the picture of the Big Bang is a picture, is an idea, is a concept of the universe in which we live. And all of the Big Bang started as mathematics. So you see, mathematics not only constrains us in certain ways, it tells us what can be parts of our imagination that can never be in reality, but it also opens our eyes to possibilities of things that we could never think of. Another such possibility is telecommunications. We use radio waves and radar waves and television waves to talk to each other, microwaves. And yet, until a physicist named James Clerk Maxwell imagined such a thing, no one could do that. You have to have the idea often in order to make the attempt. And so this is the thing that is empowering about mathematics. Our universe has many other attributes. We have mass. We talked about those neutron stars. Well, in our universe, even more bizarre things exist called black holes. It will turn out, as we tell the story of string theory, that black holes play a very important role in convincing the physics community that something like string theory is absolutely necessary. So that's a future part of our story about string theory. What about the strings themselves? Well, let me show you one other picture as we close this lecture, a few other pictures of strings as we close this lecture. If you want to imagine a string, the simplest picture I can give you is think of a piece of spaghetti, a very tiny piece of spaghetti. Well, if it's really a piece of spaghetti, or maybe a substance that has a little bit more tension, you can take it and you would be able to pluck it. And so whatever these tiny filaments are, you would expect that if they behave like strings in our world, they should be able to sing. So here we see a singing string. We'll have to explore how this comes about. When strings were first written as equations, it was realized that two types could exist. There's one type of string where the ends are free to flop around. That's called an open string. Another type of string, you take the two ends and tie them together. And that's called a closed string. So if this thing is a piece of spaghetti, then clearly the one at the lower right is a spaghetti-o. So that's where we're going to be headed in this series of lectures. We want to understand why physicists have come to these very strange pictures about how the universe is put together and how it fits with real science. Now, to do this, let me again make the point that string theory is mathematics. Now, I'm sure that you in the audience did not sign up for a course to become a PhD in mathematics. You want the information. And it turns out that there's a way that I can get that information to you, which is how such a lecture can be given. Most of you looking at these equations will say, well, gee, that might remind me of calculus when I was a freshman in college. You'll see an integral sign here. There are derivative operators, and these things called x are functions. And so this is what a string theorist actually does. We don't sit down and produce pictures, we actually produce the mathematics. So from where do these pictures arise? Well, it turns out that science, and in particular theoretical physics, has kind of a Hollywood attribute about it. What do I mean by that? Well, if you've been to the movies recently, perhaps you've seen marvelous computer graphics in something like maybe Spider-Man or the Hulk or Lord of the Rings. And in these movies, there are images of creatures and places that don't actually exist. So how do these images get on the screen? The answer turns out to be it's nothing but mathematics. You see, a computer is a device that lets you play mathematics in precisely the same way that musical instruments play music. And so for a string theorist, we do the mathematics, but it generates pictures in our minds. These pictures are things that we can communicate to everyone else. But this did not start with string theory. This process of having pictures related to equations has been around as long as there has been science, and in particular as long as there has been physics. Whenever a physicist writes an equation, in the back of our minds, we typically have a picture of something going on, some sort of situation, like the waves that I showed you, or perhaps the string that I plucked. There's a picture that the mathematics is describing. And so the way that physics proceeds is, on the one hand, we build these pictures. That's sort of in the realm of our imagination. On the other hand, we must write equations that support the way these pictures work and evolve. That tying of the mathematics becomes critical there. And often the mathematics actually provides us with other surprises that we'll talk about in the next lecture also. And so this is the realm of string theory. Well, what else can I tell you about string theory that's of some interest while we're getting a preview? Well, these pieces of spaghetti have other attributes which will be very important for our future lectures. One of these attributes is spin. In our world, if you go to a science class, a teacher will tell you, well, an atom consists of protons, neutrons, and electrons. Let's concentrate on the electron for the moment. It turns out that if you want a picture of an electron, well, it suffices to think of a small ball. And so you can see such an image in my animation. And on the interior of the protons and neutrons, there were these smaller pieces of matter. They're called quarks. Well, we could think of this ball perhaps as one of those objects. In either case, in the case of a quark or an electron, both behave like small spinning balls. Now, this has been known since the 1930s when we discovered that tiny objects always spin. It's a very peculiar spin. You can't speed it up, you can't slow it down. It always goes at the same rate, either clockwise or counterclockwise. So that's a property of the real world. And as I said, in the 1930s, physicists learned with mathematics how to describe that property. Suppose we now turn to the realm of our imagination. Can we incorporate this spinning property into our pieces of spaghetti? The answer turns out to be yes. This will lead to a second generation of strings. These are what are called spinning strings or superstrings. So not only does the pasta sit there and vibrate and jiggle, but it also, in some sense, spins on its axis. So in a future lesson, we'll come back and find out why this is such an important observation about string theory. Let me take you to perhaps one of the most interesting and most well-received attributes of string theory. So we can imagine that the string is an object that I can hold here in my hand, and it vibrates. In fact, we don't have to imagine. I have a computer animation of a vibrating string on this particular plot. You'll notice on the left-hand side that I've chosen a closed string and it's vibrating. But if you look very carefully, you'll see that not all of the string is moving. The places where the red dots sit are at rest. So even though the string as a whole is vibrating, there are these special places which physicists call nodes that are at rest. Before 1984, all physicists in the world thought that closed strings had to have this behavior. But once you understand that this behavior is there, you can let your imagination take over. The mathematics says this: can you imagine something different? In 1984, David Gross, Emil Martinek, Ryan Rohm, and Jeff Harvey at Princeton University imagined a different kind of string. What's different about this picture? Well, if you look very carefully at the nodes, the red dots, you'll see that they're now in motion, whereas in the previous picture, they were fixed. So if you can write the mathematics that describes this, you've described a new kind of string. Well, these are rotating in a clockwise sense. If I can do that mathematics, can I write the mathematics that makes it rotate in a counterclockwise sense? The answer is yes. We see it here in the picture. The four gentlemen at Princeton in 1984, which we now call the Princeton String Quartet, first wrote these equations that had all these motions. And when they did this, a most marvelous thing happened. This is called heterotic string theory, and we'll come back and visit heterotic string theory in the future. But when heterotic string theory was written as equations, it became absolutely clear that a dream of Einstein had been realized. Albert Einstein was perhaps the greatest physicist who has ever lived. At least some would argue that. However, the last 30 years of his life were extremely frustrating. He spent those 30 years looking for something he called a unified field theory. Now, what's a unified field theory? Lots of words there. A unified field theory is a piece of mathematics that must describe gravity, must describe electric and magnetic forces. It has to describe other forces that we'll come to in later lectures that are called strong and weak nuclear forces. It must also describe electrons, photons, and all of the forces. So that's what a unified field theory is. And Einstein spent the last 30 years of his life looking for such equations. He failed. And by the time of his death, most physicists had thought that his quest was a pointless one. In 1984, the quest received a response from nature, at least in the form of mathematics. The Princeton String Quartet wrote equations which proved that Einstein's 30-year-long quest was not a quest in vain, not Don Quixote wandering in the wilderness, but in fact was a vital piece of science. A unified field theory in the form of heterotic string theory was written down. Now, there are other interesting attributes about strings that we're going to learn that make them seem even more like science fiction than we've talked about in this lecture. One of these is the notion of extra dimensions. Many of you have probably heard about string theory in various debates, programs, books, or what have you. And so you've come across this notion that there may be these hidden dimensions of our universe. Well, that may be true, but it also may not be true. It turns out that the mathematics of string theory is so complicated that although most physicists believe in these extra hidden dimensions, I and several other groups of physicists in the late 80s studied the equations and found that there are versions of string theory in which there are no hidden dimensions. So which is right? Well, in science, there's always one arbiter to the question, which is right. That's Mother Nature. And so for string theory to become a true piece of science, we have to have a signal from Mother Nature. She has to tell us in some way that this is the mathematics that describes the way that the universe works. We are hoping, many of us who have spent our careers working on this mathematics, because as you can imagine, stuff is really hard. Don't let anyone tell you it's easy. It's really hard stuff. But it's probably no more hard than becoming a concert level musician. And many people do that. People learn to play the violin. People learn to conduct. And in some ways, being a theoretical physicist is very much like being a concert musician. So we're going to come back to this connection of music too, because that's a very strange thing that's going to empower us in these discussions of string theory. So this is the realm of strings. This is what we're going to be doing in these 24 lectures. I'm going to be talking about mathematics on one hand. I'm going to be talking about science on the other hand. I'm going to try to knit them together in a coherent picture so that all of those who are listening to these lectures can have more insight into what's going on, this very strange boundary called superstring M theory.